Assalamualaikum warahmatullahi wabarakatuh, and good day everyone. Okay, so today we will continue our lesson in a new topic, which is in a computational fluid dynamics, or what we call it as a CFD. Okay, so what is CFD actually? Okay, so and what we learn in CFD topic. Suppose that student who take the PSM topic related to the CFD need to know more details about this topic, right? So what is a computational fluid dynamics means? So it's a prediction of the fluid flow which involves heats, mass transfer, phase change, chemical reaction using the computer software. Okay, so actually it's a fluid analysis using the software. Okay, using the software. So in other words, CFD is a branch of fluid mechanics that use numerical analysis and data structures to analyze and solve the problems that involve fluid flows. Okay, so it's not exactly we are focusing on the fluid, we are also focusing on the air. Okay, but more related to the air and also the fluid. Okay, so in automotive there are very many sectors that use the CFD analysis in their environment of work. For example, in the automotive sector, okay, Daimler Chrysler is the pioneer. Okay, is the first company to use CFD in automotive sector, which is focusing on the flow analysis of the vehicle in order to calculate the drag coefficient, the heat flow in the engine bay, for example. So there's an example of the CFD in automotive. And also Speedo. Okay, Speedo here. Speedo is the first swimwear company to use the CFD analysis. So this is a what is a computational fluid dynamics means. Okay, basically many areas or sectors already involved in the CFD analysis. For example, like I said before, is automotive, and then the building structures, in the transportation. Okay, so many more. They already, the CFD analysis already known in the these sectors. All right. So next. Okay. So basically, in studying the fluid flow, we have three ways, okay, to study the fluid flow. First is experimental fluid dynamics. Okay, so what is experimental fluid dynamics? So it's more focusing on the experiment way, which is the actual ways to study the flow. Okay, so this is for example, this figure is actually the how we want to study the flow for the vehicle using the wind tunnel. Okay, so this is an example of the wind tunnel. So in order to see the drag coefficient of the vehicle, so we need to do the experimental study on that vehicle, the prototype vehicle. We are placed in the wind tunnel. Okay, it's wind tunnel or smoke tunnel, and then we can see the flow, the air flow of the vehicle, whether the drag coefficient is higher or not for the shape of the vehicle. Okay, besides that, we have a theoretical fluid dynamic. So it's a mathematical equation to calculate the fluid dynamics. Okay, the theory. So you already learn for the subject fluid mechanics, okay, or thermodynamic, or in your case maybe you already learn thermofluid. Okay, so this is the theoretical calculation behind the CFD. Okay, behind the CFD. And now we are focusing on the computational fluid dynamics, okay, which is related to the software. We are using the software to calculate the fluid flows. Okay, it's not using the experimental, it's not using the theoretical fluid dynamic, which is a mathematical equation, but we are using the software. Software will calculate you the fluid flow, the drag coefficient, the thermal analysis. So all the computational fluid dynamic or CFD analysis will do in a software. That is objective of what you learn in a CFD, right? Alright. Okay, this is the type of the CFD analysis. There's several type that, for example, this CFD analysis. The first example is a turbulent model. Okay, this is a flow analysis of the cylinder. Okay, cylinder. And the second one is the wind turbine blade. Okay, how we want to capture the wind turbine blade. Okay, the wind turbine blade. How the flow of the wind if they hit the turbine blade. Okay, so you can see how the wind flow here. Is it the shape, the design of the wind turbine? Is it exactly can solve the wind turbine problem or not? Or you can use in the CFD is a cooling. Okay, you want to study the cooling system in your vehicle, the engine cooling. Okay, how the thermal analysis in your engine. So you can use this software CFD analysis to study the engine cooling, the thermal mapping. Okay, this is a transient SCI cooling. And then you can also study the velocity and the pressure field for the vehicle. Okay, for example, this is a race car. Okay, you can study the flow, like I said before, the drag coefficient, the wind flow analysis. Okay, and also you can calculate is it the shape of the vehicle is okay or not, suitable or not to get the ideal performance of the vehicle. Right. So next is a fluid structure analysis ataupun fluid structure interaction ataupun FSI. So the formation of the rotational rod sign, okay, under the wind loading. So we need to know the FSI analysis. Is it, if we put the signage here, do you have a wind, the heavy wind? Okay, is it okay or not? Okay, so we can calculate and we can analyze using the CFD analysis. Right. Okay, so this is a family of fluid mechanics. Okay, you already learned about the fluid mechanics here. You still remember that the fluid mechanic, you learn the experiment of the laminar turbulence. So this is you need to revise it back. Okay, you need to revise it back. What is the fundamental of the fluid mechanic? I cannot explain it more detail. You can because you already learned it. Okay, so in the fluid mechanic you have two behavior of the fluid. The first one is the fluid static, and the second one is the fluid dynamics. Okay, so we are focusing on the fluid dynamics. You are not focusing on the fluid static. Okay, we're just focusing on the fluid dynamics. On the fluid dynamics, we have two behavior of the fluid. Okay, the first one is a laminar, and the second one is a turbulent. Okay, turbulent. So you need to know what is a laminar, and you need to know what is a turbulent. Okay, so in the laminar behavior, we have a Newtonian fluid. Okay, Newtonian fluid, and also non-Newtonian fluid. Okay, so in the Newtonian fluid, we are focusing on the ideal fluid and also the viscous fluid. So ideal fluid, you have a compressible flow and also incompressible flow. So in CFD, we are focusing on the viscous fluid. Okay, viscous fluid, we have a CFD and also the solution specific regime. Okay, so this is a family of fluid mechanics. I don't need to explain detail on that because you already learned about this in the fluid mechanics subject. So I just explain the roughly, okay, roughly about what is a fluid mechanic here. Right. Okay, in CFD analysis, we have several equation that can use to solve the CFD and problem. Okay, right. So we have several equation. For example, this is a Navier-Stokes equation. Okay, this is a Navier-Stokes equation, and then we have a Euler equation. We have a Stokes equation to solve or to calculate the CFD problem. Okay, so what is a Navier-Stokes? Navier-Stokes equation is a basic governing equation in order to calculate about the heat. Okay, conductive heat, the viscous of fluid, for example. So this is equation to use in the software to calculate the viscosity, to calculate the heat, to calculate the density, the pressure of the fluid. So this is all the item that used in the CFD analysis equation. So different version of the energy equation are possible. So here written in the enthalpy. So this is about the continuity of the fluid, momentum of the fluid, and also the energy of the fluids. I don't need to detail up what is this about, because maybe you already known in the fluid mechanics subject. Okay, for the software already embedded in the software, so you just use what is the equation that you want to use to solve the problem. Alright. Okay. Okay, next. So the Navier-Stokes equation are general. Okay, describing the majority of flows. Non-linear terms makes them difficult to solve. Okay, for certain application they can be simplified using Stokes or Euler equation. Okay, so this Navier-Stokes maybe for the non-linear terms are difficult to solve. So if you want to run CFD in the non-linear ways, okay, maybe you cannot choose the Navier-Stokes. Maybe you can choose the Stokes equation or Euler equation to solve the CFD problem, right? So this is an example of the Stokes equation. Okay, Stokes equation. So for the Stokes equation, the convective terms are neglected. So this is a convective term. Okay, small compared to the viscous. Reynolds number is low. Okay, so what is Reynolds number? You need to remember it. You need to know what is a Reynolds number. Okay, the fluid velocities are low, viscosity is large. So application using the Stokes is a creeping flow. Okay, in a lubrication or lava. Okay, or lava. So if you want to simulate the lubrication in the, for example, in the engine, how the lubrication flow in the engine, so you can use the Stokes equation, right? So next is the equation of the Euler. Okay, using the Euler equation. So in the Euler equation, viscous terms are neglected. So this is a viscous term. Okay, so this is a viscous term. So we are neglected that because the wall effects are too small. Okay, are too small. So applicable when no solid boundaries in the flow domain. So the combination Euler equation in the far field. Okay, boundary layer equation including viscous effect near the wall. Okay, so application when we when we want to use the equation of Euler. So basically in the aerospace domain, so obtain the pressure loading, gas dynamic or shock wave. Okay, this is basically application when we want to simulate in the aerospace domain or the gas dynamics. You can use the Euler equation, right? So you can use this equation for this. So don't be afraid with this equation. We cannot calculate it. Okay, you're just using the software to simulate the CFD analysis. Alright. Okay, CFD solver technologies. Okay, solver means that you how we want to simulate, we want to run. Okay, there are several solver that you can use. Okay, so in the primary technologies, okay, primary technologies, we have a finite difference. Okay, finite difference using the Phoenix cam. We have a finite volume. You can use software Star CD, Fluent, SC Tetra, CFD++. Okay, in a finite element. Okay, you have a Flowtran, feed up, Glucking. This is Accusoft. Okay, so basically in this subject we are focusing on the finite element analysis using the CFD, and we are using the Accusoft solver. Okay, using the Accusoft solvers. And others is we have a panel method, aerospace codes for external aero. We have a spectrum method, Necton polyflow, and lattice Boltzmann. Okay, so this is other application solvers. Okay, but for this subject, especially in automotive, we are focusing on the finite element and also finite volume. Okay, but in this chapter we are just focusing in the finite element using the Accusoft. Alright. Okay, so this is a fluid motion. Okay, fluid motion. I'm not going to explain detail about it. Okay, just explain roughly about the fluid motion. The fluid motion, we have a translation. Okay, motion of the center mass. So this is a motion of the center mass. Right. So using this equation and dilatation. Okay, we have a change in volume using this equation. We have a rotation about 1, 2 or 3 axes. Okay, and also shear strain. Okay, so this all 4 is a fluid motion. Okay, fluid motion, you can move about translation, dilatation, rotation, and also the shear strain. Okay, say compressible and incompressible fluid. Right, so fluid can compress and incompress. Right, a fluid flow is said to be compressed when the pressure variation in the flow field is large enough to cause substantial change in the density fluid. Okay, what means by that? Okay, what means by that? It means that when the fluid is compressed when the pressure variation is too large. Okay, the pressure outside the fluid is too large, so it means that the fluid is compressible. Okay, the mean is compressible. An incompressible flow refers to a flow in which the material density is constant within a fluid parcel. Okay, so this is an example of the compressible. So this is a fluid. Okay, this is a fluid. When it's we have a gap, small hole to go through the fluid, it will compress. Okay, it will compress. Right. Okay, so viscous and the inviscid fluid. Right. In a viscous fluid, the fluid friction has significant effect of the solution. Okay, where the viscous force are more significant than the initial force. Right. So this is an example of the equation. The viscosity of the fluid is equal to 0. Right. In viscid flow has many applications in a fluid dynamics. Okay. Alright, so this is a Newtonian fluid and non-Newtonian fluid. So what is Newtonian fluid? Newtonian fluid is a fluid in which the viscous stress arising from its flow at every point and linearly proportional to the local strain rate. So what is meant by that? So basically Newtonian fluid is a fluid. We're focusing on the viscosity. So viscosity is a constant here. Okay, viscosity is constant. We can refer it in as a in the this graph. Okay, graph about shear stress and also the shear rate. Okay, so what means by this? So based on the Newtonian fluid, the stress, okay, the stress is directly proportional to the rate. So it's give a linear. It's basically about more likely about linear region. Okay, because it's the rate, shear rate is directly proportional to the shear stress. Okay, and the viscosity is a constant. Okay, and a non-Newtonian fluid is a fluid that does not follow Newton's law. This means of viscosity. This means that the viscosity is not constant, and also the shear rate, also the shear stress is not directly proportional. So basically it's about the Newtonian fluid and also the Newtonian non-Newtonian fluid. Right. So what is a lamina and turbulent? You already know about this term. Okay, what is a lamina and what is a turbulent? So lamina is a fluid flows in a parallel layers. Okay, parallel layers with no disruption between the layers. So basically the fluid in a lamina condition is a steady. Okay, the steady state. It's no disruption from outside. Okay, so the fluid is in the steady state. So for the turbulent fluid, okay, the fluid flow is in which the fluid undergoes irregular fluctuation or mixing. Okay, fluctuation and or mixings. The speed of the fluid at the point is a continuous flow undergoing change in both magnitude and direction. So in other words, turbulent fluid, the fluid is have a higher speed, okay, and the behavior of fluid is not a steady state. It's not a steady state. Okay, so this is a example figure of the lamina. Okay, this is a lamina. The fluid is in the steady, and also the turbulent. Okay, the fluid is not in a steady state. Right. So turbulent. Why is turbulent model is important? Right. The turbulent determines the point of the flow separation. Okay, the flow separation. Okay, same boundary condition, different turbulent model. Okay, we have a, for example, this is a ball here. We have a fluid or air here. Okay, so when the air or fluid hit the ball, okay, so it gives from the steady state of the condition, you can when it hit the ball, it can show the turbulent. Okay, this is a turbulent, or this is a turbulent. Okay, so unsteady, aperiodic motion in which all three velocity component fluctuation, missing matter, momentum and energy. Okay, different separation point, different flow pattern, different performance. For example, it's a drag coefficient of the car, lift coefficient of the airfoil. For example, we have a car. Okay, we have a car here. Okay, I just draw it. So when the wind hit the, for example, we have a spoiler here, hit the spoiler, the wind flow from the steady state, when they hit the spoiler, it will give the wind turbulent. Okay, it will separate. Okay, it will give us separation point here. So this is what we call this a drag. Okay, drag coefficient. Okay, turbulent flow is a chaotic, diffusive, dissipative and rotational. Alright. Okay, next we go to the turbulence, which is numerical models. Okay, we have a several type of numerical model in turbulence. Okay, in CFD we are focusing on the turbulent situation. Okay, turbulence, it's not the lamina, but we are focusing on the turbulent. So first is a direct numerical simulation. Okay, direct numerical simulation. For direct numerical simulation, no turbulence model is used. Okay, we are not focusing on the turbulence. Okay, resolve all scales in space-time. We have a fine mesh, small time step, and very time consuming. Just a little bit time to run this simulation, and useful tool for fundamental research in turbulence. So develop, validate new turbulence model. Okay, so this is how the direct numerical simulation, right? Okay, and then next we have a unsteady, which is a transient or steady. Okay, unsteady or steady in a transient mode. Okay, turbulence is by definition unsteady. Okay, turbulence is definition steady, often interested in mean values. Okay, you mean and or the fluctuation. From a statistical point of view, you can see it's in a steady state flow. Okay, so this is a transient modes for the numerical model of turbulence. And then next we have a Reynolds average Navier-Stokes equation. Okay, this is another type of the numerical models, which is a time average equation of fluid flow, years average flow quantity steady state. Very popular approach. Okay, basically this is this approach of a numerical model. Basically you will use this Reynolds average Navier-Stokes in the CFD analysis. Okay, it's a very common equation that use. Okay, common model, we have a K epsilons, we have K omega SST, and also Spalart-Almaraz. Okay, so this is common features. Okay, you can use what terms do you want to solve in the equation. Either you want to use the Spalart-Almaraz equation, K omega, K epsilon, SST, for example. Okay, and wall function are used to model velocity gradient near the wall. Okay, we need to build the wall. Okay, we need to build the wall. Advantage, no extremely fine mesh near the wall, but first layer thickness has to be in the certain range. So we need to build the wall of the fluid flow before we run the CFD in the certain object, right? Okay, and next we have a large eddy simulation. Here is a large eddy simulation. No time averaging, filtering in time and space. Large scale phenomena are simulated in transient manner. Small scale phenomenon are modeled. Better result than before this, which is a Renault because some parts of the turbulent fluctuation are simulated, popular for aeroacoustic. Okay, if you want to simulate in the aeroacoustics simulation, so you can use the large eddy simulation. Okay, large eddy simulation. Okay, and then next is a detached eddy simulation, which is a DES combination of the runs and also less, so close to solid boundary, less approach, different requirement for grid. Okay, this is I not to state the detail. So this is some example of the turbulent numericals models, right? So this is pyramid views. Okay, pyramid views for the computational time modeling, right? So this is a computational fluid dynamics parameters. What is the numerical model? We have runs, Reynolds average neighbor stock, we have a large eddy simulation, and also direct numerical simulation. Okay, we are going up. Okay, the modeling is means is quite simple. Okay, simple Reynolds average neighbor stock is simple modeling. Okay, compared to the direct numerical simulation or large eddy simulation. Okay, but become towards the back, okay, or the bottom, the computational times become more longer. Okay, for example, if you use the direct numerical simulation, it take a longer time to simulate compared to the runs. Okay, compared to the Reynolds average neighbor stock. Okay, for Reynolds average neighbor stock, we are just focusing on the wind flow, but for the large eddy simulation, you can use the large scale turbulence, and for the DNS or direct numerical simulation, all turbulent scales. Okay, all turbulent scale. Okay, if you want to have a simulation with you want to see more parameters on the turbulence, you can use direct numerical simulation, but the computational time is take more longer to run the simulation, right? Okay, so before you run the simulation, you need to mesh. Okay, you already know about how to mesh in the hypermesh, so you need to meshing the model before you run the CFD simulation. So same, it's a pre-post step. Okay, pre-post, but it's quite different compared to the finite element analysis. If you want to run the linear static or non-linear analysis, the meshing is quite different compared to the CFD meshing. Okay, compared to the CFD meshing, because in the CFD meshing, the fine mesh is more focusing on the area that the fluid is higher. Okay, the fluid flow is higher. Other than that area, you can roughly mesh. Okay, the element size can put it bigger, but in the focusing area of the fluid flow, okay, you need to do a fine mesh, which is the element size is quite small in order to capture the fluid flow. Okay, grids can either be structured or hexahedral or unstructured tetrahedral, so depends upon the discretization scheme or application. Okay, so you can use the scheme finite different or finite volume or finite element. Okay, so this is a structured, and also this is a unstructured. Okay, unstructured here, and also this is a structured. Okay, you can see the structured view here. The application thin boundary layers best resolved with highly stretched structured grids. Unstructured grid useful for complex geometries. So boundary layer elements are important to capture near wall physics. In AccuSoft, we can simulate boundary layers also by a tetra elements insignificant to the element. Okay. Before you run the CFD solution, you need to set up the pre-processing model. Okay, you need to to set up, to mesh, set up the boundary condition, to set up the flow, when you want to flow, outflow, inflow. There's a, you want to do the pre-processing before you run the CFD simulation. Okay, so this is a common boundary condition that you need to know and you need to set in your model. The first is the inflow. Inflow, what's it mean by inflow? Inflow means that where the fluid or air want to take in to your model. You have, for example, you have a pipe. For example, we have a pipe here. Okay, we have some pipe here. So let's say that the air or fluid will come here. Okay, so you need to set this region. Okay, you need to set this region is a inflow. Okay, as a inflow. Inflow means that where the fluid or air start to take into your object. Okay, so in the inflow you have to set the volumetric flow rate, mass flow rate, inflow velocity, pressure or temperature. Okay, so next is a outflow. Okay, outflow, what's mean by outflow? When the fluid or air take into your parts, okay, then it will move in your part and then it will go out. So go out means is a outflow. So this region, okay, this region is a outflow. Okay, is a outflow, mean by outflow. So you need to set in your simulation where is the inflow area and where is the outflow area. And then we have a wall. Okay, wall is a moving wall. We have a moving wall, for example, road or external arrow, rotating walls or temperature. Okay, so where is a wall here? Wall is a here. Okay, this is a wall. Okay, this is a wall. Okay, this is a wall. For example, the pipe here is a, this is a wall. Okay, so this is an example of the what is mean by inflow, outflow, and also the wall. Okay, and then we have a boundary layers. Okay, we have a CFD grid, boundary layers. What's mean by this? Okay, boundary layers are multiple layers near the wall. Okay, be careful with the first layer thickness, exponential growth rates, smooth transition between the boundary layers and also the tetras. Okay, this is a boundary layers for the flow, inadequate, better. So you need to set the boundary layers for your object. Okay, boundary layers for your object. And we have a tetra mesh. This is a meshing setup. Tetra mesh. So the growth rate must below than 20%. We have a local refinement. What's mean by local refinement? Yeah, like I said before, in the critical area we need to refine the mesh. Okay, we need to use the small size of meshing elements so that it will capture the critical area. Okay, we have a coarse mesh in the far field. Coarse mesh means that in the not critical area we can roughly mesh it in a bigger size of element. So it means it is a coarse mesh. And we have a hexa mesh. Okay, hexa mesh, pure hexa mesh, difficult to generate, limited flexibility regarding refinement, and still popular for turbines and wind tunnel. Okay, so basically hexa mesh, we are using hexa mesh for the wind tunnel only. Okay, wind tunnel. For example, this area, wind tunnel. It's not for the object. It's not for the car. For just only for the wind tunnel. And also the combined mesh. Okay, you can use different element types. Keep element quality and transition in mind. Okay, we have a tetrahedron, pyramid, triangle, hexahedron, and many type of the elements for 3D meshing. Okay, 3D meshing. Right. So this is a CFD grid. And initial or boundary condition. Okay, so initial condition, we have to set the pressure and also initial velocity at all points in the flow. Okay, so before you set the boundary condition, you need to set what is the initial condition of the object, what is the initial pressure for the fluid, and also initial velocity of the fluid. Okay, and also the boundary conditions, you need to set the walls, inlets, outlets, largely specify what the solution will be. So like I said before, you need to set up the walls, you need to set up the inlets ataupun inflow, and you need to set up the outlets or the outflow, right? Or the outflow. So this is a CFD process. Okay. Then next, for the lab practice for the CFD, you need to follow this CFD process in order you to set up the pre-processing of your model, and then you need to run and also analyze the result. Okay. So first, you need to use the geometry setup. So you define the geometry. Volume occupied by fluid is discretized in a different cells, and also physical modeling is defined. Okay, and also boundary condition are defined. So these four you need to set for your geometry, for your object, in order you to run the CFD. Next, you need to assign the parameters. Okay, you need to define specific behavior of a fluid, interference and interaction at the boundary, and check whether the problem is steady state or transient. Okay, so in the software you can choose whether you run the steady state, or you can run in a transient. And also next is a solution. Okay, solution, you can analyze and visualization of a resulting solution. So first you need to do the pre-post. So this is a pre-post. Okay, this is a pre-post, and it's a post-processing. Okay, pre-post means that you need to prepare the object, you need to mesh, you need to set up the boundary condition, you need to set up the parameters, and then you run, and then you can check the result in terms of the flow, in terms of thermal, in terms of temperature, in terms of drag coefficient, for example. Right. Okay, important elements in the CFD analysis. So what you need to know in the CFD analysis, the first is the geometry. You need to enclose the volume. Okay, enclose the volume or water type, mesh, surface, or volume. Okay, so this is about the meshing. Okay, I will teach you details on when we do the lab practice. And next, you need to define what is material properties, whether you want to choose the fluid or solid. Okay, fluid is a fluid, whether you want to choose the solid. Okay, and then next is a boundary condition. We have a global, we have a local. Local is a model, global is a surrounding. Okay, model, local is specific on the object, global is a surrounding of the object. And we have to define a solver, what type of equation. I already explained different type of equation. We have runs, lengths, for example, and then you can choose whether you want to choose what type of equation that you want to use, and also the analysis type. Right. Okay, so that's all for introduction of and theory of the computational fluid dynamics. I will explain detail on the video regarding the lab practice on the CFD. Okay, so what it means by the turbulence, setup, boundary condition, all that thing in the lab practice video. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.